Okay, so we'll just see what we did last class before we proceed. So what, we started off with the one-stage op-amp. We looked at the noise of the one-stage op-amp, right? That happened to be 16 kT over 3 over GM into 1 plus GM3 over GM1. That is the input referred noise. Then we looked at the input referred offset in terms of the VT mismatch. And of course, it had the same similar kind of dependence as the input referred noise, right? Okay, and then we discussed a very important parameter of the op-amp, which is the slew rate. So which is simply the, for a large input differential input step, what is the maximum current the op-amp can source into a capacitive load, correct? And so for small signals it's just related to the GM, but for larger and large signals eventually the maximum current you can source is I0. So I0 over C happens to be the slew rate. Okay. Then we looked at the positive and negative swing limits of the op-amp. So input and output. And then of course, just quickly we discussed the bipolar, but that's just an aside. Okay. So what we'll do today is we'll discuss the other type of one-stage op-amp, which is called the telescopic op-amp. Okay. Okay, so this is based on the Cascode topology, and this is also a single stage op-amp. Okay, so we know if I just take a Cascode transistor, by now we know a lot of things. We know what is R out. So let me call it 1 and 2. So it's GM2 RDS2 times RDS1, and of course that is the approximate expression. The actual expression also has some other terms like RDS2 and RDS1, but which we usually ignore because there's enough gain through the op-amp. Okay. What can VB be? It can be as low as VDSAT1 plus VGS2, okay, which is approximately VT2 plus VDSAT. Now, right now I have assumed that the VDSATs are equal, which in reality may not be true, okay, but we'll assume that way. Second thing you need to remember, VT2 is not the same as VT1 because of the backgate effect. Right now, remember that the bulk is going to be connected to ground for the NMOS in most cases. Okay. Now the other thing we know very well, if you have a parasitic capacitance at this node, where can you get the parasitic capacitance from? Plus CGS2 plus CDB1, right? Those are the largest sources of parasitic capacitance. So you have the gate source capacitance of 2 and the drain bulk capacitance of 1. Okay? Sorry. Yeah, CGS. Sorry? You have CGS2 here and CDB1 here. Correct? Right? You have CGS2, right? Between and the gate is signal ground. Correct? Okay. So this is the parasitic capacitance, and we know that a lot of things happen with respect to frequency. So for now we'll ignore it, but you need to keep this in mind always. Okay? Which is, for example, the output impedance can be a function of, we have assumed that the impedance here is RDS1, but as frequency increases, we know that capacitance will have an effect and so on. Okay? But one thing we can clearly say, the minute you add a cascode, you're creating an extra node, right? So now that node will actually have a pole associated with it. So the minute you go from a single stage to a cascode op-amp. We'll look at the cascode topology shortly. But one thing you have to remember is you're introducing a node which has a parasitic capacitance. And what is the impedance at this node? It's approximately GM1 over GM2. Correct? So you will most probably get a pole at GM2 over CP. Correct? And you'll get this at every cascode node. So every time you add a cascode, wherever you add a cascode, you'll get this. Correct? But we also know that this is, so let's say you want to compare this with the original, let's say single stage op-amp. Right? Why do we want to go to a cascode? We want to increase the output resistance. Why do we want to do that? We want to increase the DC gain. Why do we want to do that? Because we want to reduce the steady state error. Right? We want to make it more closer to an ideal transconductor. Correct? Okay. So you can also do the same thing by increasing the length, arbitrarily. But what will happen is the actual capacitance. So let's say you just had this transistor and you keep increasing the length. The parasitic capacitance will increase a lot more. So actually the pole will become quite small. Okay. So that is something you have to worry about if you just work with a single stage op-amp. Whereas here you can create a very large output impedance while adding a somewhat prominent dominant pole. Okay, we'll need to see. Okay, only if you analyze it, you'll see if it is really dominant or not. The other thing you'll note is most probably so far we have assumed that VI is actually ideal. Okay, in many cases it may or may not be true. So you will have some other circuit which has some output impedance which needs to drive this input capacitance. So in reality, if you have a cascade of blocks, you'll probably have a pole associated here. And one difference between the cascode and the normal one is that here, what is the input capacitance? CGS1 plus, in this case, approximately equal to CGD1. So now we'll look at the effect of CGD1. What does CGD cause? If you take a normal common source, you have a very large gain from input to output. Correct? So the capacitance CGD gets multiplied by the gain and appears at the input. Right? So the input capacitance can be quite prominent. Whereas in the case of the cascode, what is the gain from input to here? It's GM1 over GM2, which would be very small. Okay, in this case I've assumed it's 1, but it would be very small definitely. So in other words, the input capacitance is also better for the cascode topology. Okay, so now let's take a look at what it will look like. So what we'll do is we'll take the single stage op-amp, and what we'll do is we want to increase the output impedance, right? So where would you add the cascode to increase output impedance? So that was for a single stage, right? Just for a common source, you know how to increase output impedance. If you go to a single stage op-amp, right, which has more number of devices, where would you add the cascode? Where? Current mirror. Okay, so maybe you can start adding it there. So let us say we replace this guy with a cascode current mirror. Okay, so if you do that, what is the output impedance? What is the output impedance right now? Without any cascodes? It's just RDS4 in parallel with RDS2 in this case. Correct? If I add a cascode for the current mirror, what is the output impedance? RDS2 in parallel with, it's just RDS2. Okay, so it's RDS2 in parallel with, you will have a GM RDS times RDS4, right? Okay. Right? So now you see, obviously you have to add cascode devices for both sides, both up and down. Because for a starting point, let's assume that the two RDSs are equal. Okay. If you have a certain gain with a single stage, if you add a cascode only on one side, the gain just becomes double. Okay. Earlier it was RDS by 2. Now it just becomes RDS. So you just increase your output impedance by 2 and gain by 2. So in reality, you have to add cascode devices on both sides. Okay, I'm running out of space. I'm going to move it to the next page. Okay. So now, what will you do with this node? Right? Just like you had a normal diode connected transistor, now you can make a high swing cascode. Correct? This will be your output. Correct? So let me call this C. Okay. So the cascode gates are biased at some VBN and VBP. We know how to generate these things. So we'll ignore it for now. But yeah, so we know how to generate them, right? We have looked at this before. Yeah. So we know how to generate VBN and VBP. Okay. So suppose you need to write the poles of this op amp. So now we know we are going to get poles, right? So where all will you get poles? So what happens to this pole? First of all, the current source at the current source node, it's going to be the same as before. Okay. So to a large extent, you can ignore that. You'll get a pole here. We already had a pole there, so we have at the current mirror node, we're going to have a pole here again. Right? You're going to have one here, one at the output node. Let me call this P1, P2, P3, P4, P5, and P6. Okay? We have 6 poles. What do we want? We want P6 to be the dominant pole. Correct? Is that right? Okay. In the earlier case, in the single stage op amp, we had one, let's go back to that, we had one non-dominant pole here, correct? And what else did we have? We had one dominant pole, one dominant non-dominant pole, and what else? We had a 0, right? Because of the, we had 2 different paths, right, to the output, so we also had a 0. So what do you expect here? How many poles and how many zeros do you expect? Okay, so let's assume first of all that C is quite large. So we'll assume that output P6 is the dominant pole. Let's assume that. Okay. So what is going to be the next dominant pole? The most important of the non-dominant poles. P3. Why? Sorry? Impedances? At P3, the impedance is very high here. Why is that? It's actually very low, right? Okay. What are the impedances? What are the impedances at P1, P2, P3, P4, P5? They are also quite low because you do have sources, right? So all of them are, that is one good thing. All of them are low impedance points. So the poles are going to be a little bit far out, right? If you have a high impedance point, you have a very small pole, dominant pole. If you have a low impedance point, you have a non-dominant pole, correct? So that is a good thing. So what can you tell me about the relative positions? Out of these, let's say out of these 4, out of these 5, so P1 to P5, which is going to be important and why? P3, why? right? You're going to have, similar to the earlier case, you're going to have a large capacitance, which is the gate source capacitance. We have two gate source capacitances. Whereas in the other cases, what do you have? You have one gate source capacitance plus a drain bulk capacitance. Correct? So if you had to look at it and say, from a high level point of view, you'd expect P3 to be the most important one. Quite possibly that's true. Okay? So I'll say number of non-dominant poles is 5. Right? P1 to P5. Is that right? How many zeros do you have? Yes? 3. Why 3? Any ideas how you would find the number of zeros? 4 zeros. 2 zeros. Why? Okay. What are the 3 parts here? I see only 2 parts. Right? Yeah, we still have only 2 parts. We don't have 3 parts here. Right? Well, how do you think P4 is going to become important? Yeah, why don't you think about it? Yeah. You have to tell me, why is P4 important? Anybody? Why is P4 important? Why don't you try calculating it out? See how P4 comes about. Suppose you calculate out the input, anyway, that's going to be one of your homeworks, right? Is to calculate from input to output, the transfer function for this. It's actually fairly straightforward. It's not that difficult, okay? So, from input to output, find out how each pole comes about, okay? Find out how P4, yeah, that's a good question. Why don't you find out? You may get some insight if you calculate it out, okay? As a homework, okay? How many, okay, let's come back to the question. How many zeros do you have? How do you create the zero, first of all? When you have 2 different paths, how do you create a zero? Huh? Different phase shifts. So what does different phase shift mean? Exactly, right? In this case, it's different number of poles. So what do? You calculate these from this path to the output. Calculate from this path to the output and add them up. If you have, in the earlier case, in one path we had no poles, in the other path we had 1 pole. So what did we get? We got something like this. This is for the single stage. Right? And this gave us a 0. What is going to happen if you have more number of poles? What happens if you have more? In this case, you no longer have just 1 plus something. You have 1 over something like this, right? So how many zeros are you going to get? Yeah, you'll probably get as many zeros as you have difference in the number of poles, right? And the pole positions, right? That's what you'd expect. In this particular case, P6 is a common pole to both sides. So that one will be a common factor. You don't have to worry about it. Correct? In the other case, you'll have 1, 2, 3, 4. You'll have 4 zeros. Right? Right? So in one path, you'll have S plus P1. That's what you have in this path, right? You have a pole at P1 and a pole at P6. Is that right? What do you have in the other paths? P2, P3, P4, P5, P6. Correct? So if you had to take the common, factor, you'll get 6 poles, which we knew. What will you get? P6 is a common factor, so you'll get 2 to 5. Plus, this is what you'll get, right? So you'll basically get a 4th order in the numerator. That means 4 zeros, right? Okay, yes. Okay. Why are P1 and P2 the same? GMs are the same. You're right. They will mostly be the same, but remember that the impedance at the drains are not the same. So in reality, in a practical case, they will be slightly different. Remember that the input impedance looking in here is approximately 1 over GM, but it does depend on the impedance at the drain to some extent. So you're right, you will get 2 very close poles. So yeah, if you ignore if you just say they're approximately 1 over GM, yeah, you'll only get 3 zeros. Okay? Sorry? Sorry? Yes, that's right. Okay? Now, remember, actually, maybe it's a better idea to do it this way. Let me redraw this slightly. You have the back gates, right? What do you do with the back gates normally? The bulk? Normally ground them for the NMOS. What do you do for the PMOS? Connect them to VDD. Okay? But in many cases, you can remember for the NMOS, you don't have a choice. Why? NMOS is a device which is directly in the substrate. Okay? You can't do anything because substrate is a global substrate. It's going to be connected to ground. You don't have any. You can't do anything about it. Whereas the NMOS, whereas the PMOS, is actually going to be inside an N-well. Right? We looked at this, the first class. So PMOS is going to be placed in an N-well, and you actually do have control over where you connect it. Okay? And there are more expensive processes where you can do the same thing for an NMOS. Right? There are processes where you have something like this. They're called like triple well processes, where you actually have and you have a P well. Okay, for the NMOS. So the NMOS is also, the bulk can be connected independently. Okay, so let's take the case of the PMOS here. So if you connect it to VDD, we know we have the threshold voltage is going to change. And to avoid that, you can actually connect it back to its own source. What happens if you connect it to its own source? Body effect is reduced. GMBS effect becomes less. Threshold voltage doesn't change. But would you want to do this? I mean, it seems like a no-brainer, right? For the PMOS, yeah, you don't, in any case, you want it to behave with a well-behaved VT. Would you do this? What do you have at the bulk here? Let's go back to the PMOS. This is your bulk node, right? So what you actually have, remember, the well actually encloses the overall device. And because the well encloses the overall device, you have a very large capacitance to the substrate, which is nominally grounded. Okay? So in other words, what you are basically doing, you're adding a very large parasitic capacitance at that node. Right? Okay? So in other words, you're actually changing the pole position, you're actually making it more dominant. You're pulling it in. Okay? So you don't want to do that. In most cases, you don't want to do that. You would rather connect it to. So remember, the well node in general has a lot of parasitics, whether it's NMOS or PMOS or whatever, right? So you don't want to connect it to a signal node because you'll be adding extra parasitic capacitance. Okay, so let's start writing down the parameters for this op-amp. What is the DC gain? What is the DC gain of the op-amp? Okay, so let me start numbering this. What numbers have I used here? So, 4, 5, 6, 7 and 8. Okay, so let me number these, and maybe I can call this 0 if needed. Okay. What is the DC gain? What is the transconductance? GM1. What is the output impedance? We know, right? It's the difference between the two cascodes. Okay, this is the DC gain, which is definitely larger than what we had before. What is the unity gain frequency? GM1 by C. Same as before, no change. So you guys are going to go home and calculate the non-dominant poles and zeros. Okay? What is the next thing we discussed? What is the offset? Actually, before we go to the offset, let's do the noise. What is the overall input referred noise going to look like? Any ideas? Double of what you had for the single stage. Why? Well, actually, what did we have? Let's go back and take a look at what we had for the single stage. We had 16 kT over 3. That is, let's look at the input referred noise. Okay, that's what matters. Right? What is it? 16 kT over 3 GM1 into 1 plus GM3 over GM1. What is it going to be in the new case? You think it's going to be double this? Why? It is going to be the same. Why is that? All the cascode transistors contribute no noise, right? In this case, I'll call it GM5. Okay? But now, there is one caveat, which is the same parasitic capacitance we talked about. If this parasitic capacitance is large enough, then it's going to be a function of frequency, right? Because the impedance now, the cascode gain of the cascode noise to the output is significant, right? Just remember that we actually worked it out in class, the dependence on capacitance. Okay? What is the offset going to look like? Input referred offset? Probably similar, okay? Because we know that offset tends to behave the same as noise, right? So probably similar. But I want you to go and work it out and convince yourself that it is the same. See, these things, all calculations take probably like 15 minutes for you, right? The poles and zeros or the offsets. Offset may be a little bit longer, right? But I mean, it's not that difficult, because at the end of the day, you have to calculate the overall offset voltage at output and divide it by the gain. It's not that difficult, okay? What is the slew rate? Again, I naught over C, that doesn't change because the bias currents are the same. First, okay, so next thing is the output swing. What do you think the output swing is going to be? Similar to the previous case? More, less? Obviously, we are going to have more number of transistors. We have more number of stacks, so definitely lower. What is V out min? What is the minimum value of V out? What is it? Anyone? 3 VDSAT. Why? Yeah, why don't you tell me what tell me with the subscript, so that I have given, right? So 0, 1, 2, 3, 4, 5, 6, 7, 8, right? So just tell me what, so you have VDSAT 4, VDSAT 2, VDSAT 0. Is that right? Okay. So that is right in a general case. However, in this, well, it's right in the sense, in this particular case, you have, this side is already biased at some VBN. Okay. If you assume that VBN is biased low enough such that these two are at the edge of saturation, then that is true. Right? If VBN is low enough such that these two guys are biased at the edge of saturation, that is true. But in a general case, that need not be. VBN need not be biased that way. You can bias VBN higher also. If that is not the case, then VBN minus VT4. Okay, that is a more general expression. Okay. What is the output V out max? V out max is very straightforward, right? It's just VDD minus VDSAT 6 minus VDSAT 8, right? Just the two current sources. Because the one difference is, on one side you have the current mirror, right? The current mirror, because it's a DC biasing circuit, you know you can bias it such that you have minimum VDSATs for the two devices. Correct? So you can bias the current mirror such that these two guys both have just VDSAT minimum and things will work fine. However, you have to be careful when you bias these guys at minimum voltage, right? Because then the closer you bias it to minimum, the more distorted the signal will be, the output signal will be. You already know that, right? So in a general case, you wouldn't want to bias this such that M1 and M2 are close to triode, okay? What is the input common mode? What is the minimum value? VGS1 plus VDSAT0, right? That is very straightforward. What about the output common mode? Sorry, what about the maximum? Not the output common mode. What about the maximum input common mode voltage? What happens if you keep increasing this? Huh? Because you have to worry about this common mode voltage, right? So it will end up being VDD, VSG5, VDD minus VSG5 minus VT1, okay, minus VDSAT3, correct? The cascode device can be biased close to saturation and that is acceptable. So this one can be biased at close to its VDSAT, okay? Okay. Now this has some interesting repercussions. Suppose you try to set it up as a unity gain buffer, okay, and I'm going to call this VBN, okay. So let's number the things 1, 2, 4, 5, 6, 7 and 8, okay. So basically I'm doing it, I'm trying to set it up in a unity gain buffer configuration. Okay, so if you want to make sure both of these are in saturation, so there are some certain conditions you have. Now that you've shorted the input and the output, there are some common mode requirements. One of them is, so I'm going to call this Vx, okay. Okay, so V out needs to be less than or equal to Vx plus Vt2, correct? That's for this guy, okay. The other condition is V out for this guy, V out should be greater than or equal to VBN minus VT4, right? So suppose, and what is Vx? We also know what Vx is. It's nothing but VBN minus VGS4. Right? So now what we can do is, now that we know, we can write, okay, so now we know Vx, we can write this and this in terms of VBN. Now we can find out the dynamic range at the output, the voltage range, minimum to maximum. What is Vmax minus Vmin? Vmax is Vx plus Vt2, which is VBN minus VGS4 plus Vt2. Okay? Minus, what is the minimum value? VBN minus Vt4. What is this? Vt2. So, VBN gets cancelled. This becomes plus Vt4 minus VGS4. What is that? What is Vt4 minus VGS4? Minus VDSAT4. Okay? This is the actual dynamic range. That is the, not dynamic range, the voltage range at the output. This is as much as it's allowed to swing to keep those two devices in saturation. Correct? What is this? This in general is going to be actually quite small. If you take some of these processors, VT4 is, VT would be somewhere around 400, 450 millivolts. Your VDSAT, let's say, it can be maybe 100, 150 millivolts. In other words, your output swing is restricted to 300 millivolts. It's quite small. Okay? So that is one consequence of adding all these device stacks. And this is particularly a problem when you do unity gain. Okay? In other cases, it may not be a big problem. What are the conditions on VBP? Again, you can write VBP conditions are pretty straightforward because we have considered, we have looked at the current mirror in quite a lot of detail. You can write out the conditions on VBP, right? That's very straightforward. I don't think I have to write it down here. Let's go back to the single stage op amp. Right? So this is your V out. What is the output common mode here? What is the output common mode voltage? It's going to be VDSAT of? Okay, so 1, 2, 3, 4, 0. Okay, so you're saying it's VDD minus VDSAT 4. Why is this? No, this is, I'm asking you, if I build a circuit, what is the output DC going to be? I'm not asking you to tell me what the maximum it can go is VDD minus VDSAT 4. That is fine. I'm asking you, if I build a circuit and I give an appropriate, let's say, input common mode voltage such that everything is in saturation, everything is well behaved, what is the output DC voltage going to be? Huh? VDD minus VSG3. Why is that? In reality, if everything is perfectly matched, you would probably expect it to be somewhere, as we said, VDD minus VSG3. You would expect it probably just based on symmetry. If nothing else, that's it. But in reality, you have to realize that the output common mode is not set well at all. Right? Because whenever you bias a transistor, you have to set the drain voltage also separately. Correct? Otherwise, what happens? If you have even a small mismatch, that mismatch gets multiplied by the mismatch current that gets multiplied by the output impedance, which is very large at that node. Correct? If you offset, a mismatch or an offset is a small signal, right? And that is a high impedance node. Correct? If you had a very small mismatch here, delta I here, it wouldn't change the voltage by that much. Right? You actually know how well it's going to change it, because it's just going to change it times 1 over Gm and you're done. And 1 over Gm is quite small. Correct? Whereas here, it can actually change quite a lot. And if you really build a real circuit, it will probably go to one of the rails depending on the mismatch. Okay, the output impedance is probably going to be high enough to send it up, either very high or very low. And same thing goes without saying for the cascode also. So in general, if you have circuits like this, you will need to apply some kind of common mode feedback to set the output DC voltage very well. Okay, we'll discuss, later when we'll discuss ways to set the common mode feedback, ways to set the common mode pretty well. Okay. Now, next class we'll look at the folded cascode op-amp. So now we are done. We have pretty much looked at all the parameters for the telescopic op-amp. We'll look at the folded cascode next class. Before that, one quick thing I wanted to cover. Okay, so this is VDD. Our generic op-amp topology included a single stage, a GM and a buffer. Okay. So question is, what kind of buffer would you use here? Let's say we had to add an extra stage. What is a normal circuit used as a buffer? A common drain, right? A source follower. Let's say we did something like this. I'm going to call this maybe X is better. Okay. What is the output swing of this? What is the maximum output swing? Or what is Vout max and Vout min? What is Vout max? So let me call this MX, MB for the buffer. Okay. So on the lower side, it's pretty straightforward, right? On the lower side is VD sat X. Correct? What about the higher side? VDD minus VD sat B. Okay. So if it had to be VDD minus VD sat B, what would node X need to be? Plus VGSB. What is that? What is VGSB minus VD sat B? VT, right? This is what it needs to be. Is that possible? Obviously not, because the previous GM stage is going to be driven by your the same supply in most cases. Okay. So what is actually the lowest, the highest X can go is probably VDD minus some VD sat. Okay, if you assume it's a single stage op amp, it's probably something like VDD minus VD sat. Okay, in which case this is wrong. So it will be VDD minus VD sat minus VGSB, which is going to be quite low actually. So if you actually put in some numbers, it will end up being extremely small. Okay, so that is why these kind of buffers are actually very rarely used. Okay, in op amps. because they really restrict your output common mode range. Okay. Okay. So anyways, we'll move on to the we'll do folded cascode next class, followed by the two-stage op-amp after that. Okay. Two-stage op-amp, there are some details. In the meantime, I again would like you to. I gave this a long time ago, but let me go there again. I wanted you to calculate this the transfer function of this of the two-stage op-amp. Right, this is the generic two-stage op-amp. Okay, I want you to calculate the transfer function of this, because maybe not next class, but the class after that we are going to discuss the two-stage op-amp, because there are some interesting details about this. Okay, so we're going to start looking at what the poles are, what the zeros are, and so on. So I want at least some of you to go ahead and, or all of you to go ahead and do this and tell me in 2 classes from now. Okay.